Okay, so this presentation is about the basics of hardware design. It's like going to be really quick and easy, so I hope it doesn't take too long. So our agenda, we're first going to start off with basic terminology, mostly regarding frequency. Then we're going to go on to resistors. I know you guys know what resistors are, so I won't spend long on them. Then capacitors, then op-amps. Then after this presentation, James is going to discuss debouncing, which is going to involve all these concepts. So I hope I can get the theoretical ideas across in a way that's pretty simple for everyone to understand. So terminology, we use omega to denote radial frequency, which is radians per second. We don't usually use radians per second, we usually use hertz. So it's frequency. And you could just convert back and forth between radial frequency and frequency. It's not that hard. There's also J, it's the square root of -1. Don't be scared. We're not going to go through this concept in detail, but just as a side note, the reason why we use J in electrical engineering instead of I is because I is reserved for current. And for the purposes of this presentation, we don't really care about the exact number, the exact frequency. We're just going to divide frequency into two groups, so high frequency and low frequency. So low frequency is like DC signal, just no variation or very, very little variation, and then high frequency, like the image on the right here. So we're going to be also discussing noise, which is just basically unwanted high frequency signals. So for most of our electrical systems, we use DC. So we don't want noise on our systems because that screws up a lot of things. So resistors, as you probably already know, it implements electrical resistance in a circuit. Sometimes it's useful to think of it as like a rock in a stream. It kind of slows down the stream a little bit. And that equation there, it's really, really, really useful, so don't forget it. So R equals VI, you've probably seen it before, but just remember it. And the main takeaway here is that the behavior for resistors in high frequency and low frequency circuits, they're the same, it's no difference. So they're going to decrease current no matter what frequency. So that's about it for resistors. I won't talk much more about them. And then capacitors. A lot of people have questions about capacitors because even if you're in ECE, you won't learn what they are until like 1B, I think. Yeah, 1B. So I'm going to start off with this, like an easy way to analyze them. So what a capacitor is, it basically stores energy in an electric field, and you probably don't care what that means at all. So you could just think of it as a tiny battery with a really, really low charge and a really, really small charge and discharge time. So you can charge a capacitor really, really quick and discharge a capacitor really, really quick. And what this does is actually stabilizes signals because it stores its own charge. So that's how it stabilizes signals. So these equations on the left side here, those don't worry about them, but in case you're curious, Z is complex impedance. So it's basically like resistance, except more complicated because it involves J. The absolute value is just 1/omega-c, and then there's some other stuff. We're not going to worry too much about them, but they're up there in case you're curious. That J is basically the reason, or the omega is actually the reason why it behaves differently in high frequency and low frequency circuits. So I want to show you a really, really easy way to think of them. So if you have a low frequency, so DC, it's going to act as an open circuit, as if the wires are not connected at all. If you have high frequency signals, they're going to act as a short circuit, so like just a plain wire. And this diagram on the right, it's a meme, just so you know, please don't take it seriously. But yeah, DC, so if, just imagine, I don't know, one of the plates here is just blocking the DC signal, and AC, it goes through like that. I've heard of professors getting really, really mad about this, so Just keep it to yourself, okay? So based on this, you now know that AC signals can go through capacitors and DC signals can't. So this allows us to do some basic filtration. So congratulations, now you're an expert on capacitors. So very, very common use for capacitors along with resistors. They can be used as filters, so they can filter out noise. Those are called decoupling capacitors. And if you want specific frequencies filtered out, you can use RC filters, so you have high pass and low pass. So does anyone want to guess what each of these circuits does? Just type in the chat or shout it out, I don't know. Any takers? Oh, one person. Just give it your best shot. No, it's not pull down and pull up. Anyone else? Good guess though. Okay, I'm gonna tell you what it is. So remember how I said high frequency signals can go through capacitors, but low frequency can't? So over here, imagine we have just a DC signal coming in. So over here, it can't go through this capacitor. So it's just gonna go through straight to the output. Now imagine high frequency. Now remember how I said high frequency signals can go through capacitors. So it's gonna go down here because it can pass through the capacitor. So what this does is actually filters out the high frequency signals. And this is called a low pass filter. And then similarly over here, for the high frequency, it's gonna be able to pass through the capacitor. But for low frequency, it can't. It doesn't go anywhere. So this is a high pass filter. It only has the higher frequencies through. So that's all it is. These things are all over the car. So it's going to be really useful to know. That's because electric cars are super noisy. They move around a lot. So there's a lot of noise generated. Okay. So next concept, op amps. This might be a lot to take in, but as long as you can remember what each of the pins does, you'll be fine. So V plus and V minus, that's the power. That's where it gets the power from. This is why we can't get infinite power from an op amp. Non-inverting and inverting and output are the actual functionality part. So if non-inverting is greater than inverting, then output is going to be it's going to be decided by this formula. And A is usually a really, really high number. So I'll just say, like theoretically, A is really high. So I'll just say A approaches infinity. So if this is high and this is low, you're going to get infinity technically, except this here is limiting it. So you're just going to end up getting V plus. And then if this is high, if this is higher than the non-inverting, then you're going to get V minus here. Are there any questions about that? I know I rushed through it really fast. Hopefully it'll make more sense after I go through some examples. So some common configurations. First one is the comparator, which is the one I just went over. So that's this one right here. That's the comparator. So if this is the input, or never mind. This is basically the example that I went through before. So V in is an input voltage, and then V minus is some reference. So this is always going to be constant. So if the input is greater than the reference, then we get a high signal. So we're going to get VCC. And if it's lower than the reference, we're going to get 0 volts because that's what's connected here and over here. Another major use for these is for sensing current. So as you guys probably remember from high school, current has to be measured in series. And this is a big challenge if you have like a printed circuit board, because that means you have to screw up the whole board, chop some parts off, and basically mess it up. So an easy way to do that, we just have a shunt resistor. A shunt resistor is just a resistor that's very, very small, so it doesn't really affect the functionality of the circuit, but it's still big enough to measure the current. So we're gonna have a voltage drop across here and across the resistor, basically. So we're gonna get V shunt, and then it's gonna be outputted. We're gonna get an output there, and then we can use Ohm's law, so I equals V over R. And so we have R, that's just this, and then V is coming out of here. So then we can just solve for I. And yes, by 0 volts, I'm referring to ground. Ground is just 0 volts. And 2 more important configurations. I'm not going to go into detail on how they work, but I'll just show you what they do. So a buffer amplifier, if you have this connected to the output, then you create a negative feedback loop, and basically V in is going to equal V out. So why would we want this? It basically isolates the input from the output. So something that I haven't mentioned about op amps is that they actually don't take any current. So the current going in and out is going to be 0. So if you need a signal out on this side, it won't affect the circuit on this side, which is extremely useful for processing signals. This is really commonly used on any input-output stuff. You could see on driver controls, this is used for any analog signals. And then another important one is a Schmidt trigger. So the symbol, this is what the symbol is on the left. And then on the right is basically how it's configured. Usually we use an IC for it, so we're not going to use the configuration on the right. But what it does, it forces the signal to either high or low. So one of the extremes is going to be either V plus or V minus. And it doesn't change the output if it's within a certain range. So I'm going to try and illustrate that. So say this is time, or say, I'm just going to say this is V in. I'll say this is V, what am I thinking? Yeah, let's do that. You know what, forget that. So say we get an input signal like this. Okay, just say that's an input signal. It's really weird looking, I don't know. But the output is going to look something like this. So it's going to go high, then it's going to go low. And over here, it's actually going to be stable at low because it doesn't go high enough. And after that, it's going to go high. So it's stable. It helps stabilize your signals. So those are all like the basic configurations. They're more obviously. If you want to learn more about them, just ask and we can give you the resources if you want to learn on your own. But that's basically it. Are there any questions? If you have any questions, just feel free to ask at any time. This isn't the only chance to ask questions, so I'm gonna move on. Oh, question. Buffer amplifier, yeah. Was there anything specific that you wanted to go over? So buffer amplifier, basically input equals output. That's the gist of it. And the reason why we do that is to separate the input circuit from the output circuit so that they don't interfere with each other. And the way the op amp does that is that current going through here and through here equals 0. So you won't have the voltages on this side messing with the signals on this side. That's how it works. Is that clear, or is there something else you want me to go over? Okay.
Yeah, the whole current doesn't go into an op-amp thing. When you do circuit analysis, it's kind of trippy, and you'll probably go over this. I guess it depends on your program, but I don't know. I find you don't really, when you're doing hardware, at least on a simple level, you don't really have to fully understand how something works. You just need to understand how the outputs are affected by the inputs. So you'll see later when I go over the project.
Yeah, don't get me wrong. It's not exactly 0, but it's really, really low because this is like super high impedance. So there's like a fat resistor right here. That's how it is. Like that's how it behaves, at least. Not how it actually is. But you don't need to worry about that. Yeah, any other questions? Oh, feel free to ask questions at any time. Congratulations, you have big brain.
I can't relate. Okay, so I guess now I'll be going over what the first part of the tutorial is, and I guess I should share screen. Are you able to let me share screen?
Yeah, here.
Okay, so which screen is it? What screen do you guys see? Do you see the slides?
Yeah, we see the slides.
If I switch, you see like the browser, right? So I can switch tabs.
Yeah, we can see both tabs.
Okay, so all right. So hardware tutorial. I'll just be going over what the project is and a few things to get started on the project. So basically, I'll kind of teach you guys what we use. So like Altium and Altium 365. I probably won't get you guys to start immediately. If you guys want, you definitely can. But I'm thinking next week we'll be doing a little more in depth into how to use Altium and whatnot. We'll be going over a bit about the background. So Nita just gave a really good presentation on like fundamentals and whatnot. So I'll be kind of explaining how those fundamentals can be applied to fix this so-called problem that we're going to be solving in the project. And then I'll be going over kind of your tasks. So I forgot to fill in my transition slides. Whoops, I will do this later. But yeah, basically Altium Designer. This is pretty much industry standard for schematic capture, PCB layout, simulations. It's called EDA. It's like electrical design application or something. I don't know. It's just a type of software, and Altium Designer is what we use. And so they have they're industry standard because they have like really good support. It's also like $7,000 to get like a license and whatnot, so you can kind of see like how strong this program actually is. We don't dive very deep into it, but it's really good to get yourself familiar with this. And yeah, we also use it to house our component library. So every project has a library of components it uses. And since we have like many different projects and different boards, we all share components. So what typically happens is for most of the board, when you're designing, you can just look through our component library and just kind of pick up components you need, because a lot of it is standard, like 1K ohm surface mount resistors, all that things. And of course, sometimes you'll need to use a less common part, in which case you'll have to add that to Altium yourself, add like the 3D footprint and whatnot. And of course, we'll be teaching you guys how to do that later. And installation, I believe Liam sent out a message over Slack for installation. So if you guys haven't done that, you should definitely get started on downloading Altium. It might take a while. And for you guys who aren't able to get it done today, I'm probably not going to go into it, but for sure between now and next week, you guys can like maybe look up some YouTube tutorials, try to start getting yourself familiar with how to use Altium and whatnot, just where buttons are, maybe some shortcuts. And if you use Apple, you'll need to install Windows by a boot camp or like a virtual machine. And I think our school offers software for that. But yeah, sorry, this is only available for Windows operating systems. But it's a really good software, so definitely something I recommend you guys do. Probably after this presentation is just the first thing is start installing Altium. So yeah, left 2 images, schematic capture. That's kind of how we lay out our, not layout, but how we design our circuits, what's connected to what, et cetera, et cetera. And then the 2 right images. The middle one is laying out the actual PCB. So your components won't be in the positions they are in a schematic capture, which is the left-hand side stuff. That stuff, you just make it to look neat and easy to read. In the middle, this is when you actually have to like move components around, draw out your traces, and decide which component goes where. This is more for optimization. Usually, you don't want your board to be super, super big, so you try to like house everything, all your components, not as tight as possible. There's of course a lot that goes into it, like signal traces. You don't want them to go too long, but you know, most traces it's okay. Some traces need to be a lot thicker because traces, by the way, are basically wires. So like when you have a copper wire connecting like a resistor to a battery, that wire is a trace. It's like a layer of copper in the board. So yeah, for example, some wires, if you have like really high voltage and really low resistance, it's a lot of current, you need to make your traces thicker. So there's a lot that goes into designing a board physically that we'll of course have to talk about later as well, but we'll save that for another discussion. And then also you can see the 3D look of the board that you designed. So you can kind of see in the middle image, there's like a square and a lot of traces that lead to it. That's a microcontroller. You see on the right, the black square and all the pins coming out, all the traces going to the pins. So you can see like in a 3D view how your board will look. And of course, you can also do what's called the silk screen, which is like labeling what each component is. And at the moment, I believe we basically build our boards by hand. So like we have bags of capacitors, resistors, our integrated circuits, which is basically anything that's a black box with a bunch of circuits inside. And yeah, we solder those onto the boards, to the pads and whatnot. And when you add new components, you'll have to like basically create a 3D file as well for this purpose. Altium 365, this is our cloud service, and this is how we do collaboration. We used to use GitHub. What we would do is we'd have like a master branch, and then for each project, we'd have sub branches, and we'd each work on that. And eventually, changes we made, we would have to push to the master branch and whatnot. But Altium offers this cloud service to us for free, and it's really useful. It's a lot easier than using GitHub, because what happened beforehand was for different projects would have different libraries of component libraries and whatnot, because they would have different parts. And then when we merged it all, it took a really long time. We'd have to like manually copy in components we added or to each library branch, for each branch library. So Altium 365, again, we'll be teaching you guys more about this in the future, but this is what we use for collaboration. And you'll probably have to talk to Ashmika to get signed up for this, but you guys won't need it anytime soon. So I guess I'm just introducing this. You don't have to worry about it too much for now, but this is where you would go to see our projects and our component libraries and whatnot. Yeah, so you can see on the side, if we select components, there's like lots and lots of files that are sorted by what type of components they are: passive components, amplifiers, sensors, etc. And under each, there's a lot of different types of components that are slightly different for each different application that we have used in past boards or that are just common components. So yeah. And then background, basically what this project will entail. Again, I apologize, I forgot to fill up my transition slides. basically, we're going to pretend that you're working on a board. The board has a push button. So this board could be like a steering board, which is basically a board that fits into our steering wheel and has buttons popping out of it. Or it could be center console, right in the middle of the car. Under our big infotainment screen, we have buttons there as well. And we find out, hey, when we press a button, the button's actually sending multiple signals. And basically what happens, actually, okay, this is a good question for you guys. Do you guys know why this would happen? So like when you go to press the on button of the car, or when we press another electrical button, and we measure the output signal, why would it switch in a manner that we kind of see on the right here? Am I able to open chat? Do I have to?
Yeah,
Okay,
you just have to click more on the side, but Jordan says it's because it's not debounced.
That is correct, I guess. But like physically, do you guys know what's going on with the button?
Why does it have to be debounced?
Yeah. Also, when I guess maybe it's because I'm presenting that I can't see chat. So
You can't see chat. If you look on the status thing on the top, there's 3 dots. Just click on that.
Yeah, I can click on chat, but nothing pops up because I think I think it's because I'm in full screen.
Yvonne says it's because of inconsistent contact.
Yeah, that's mostly right. For physical buttons, how it connects a circuit is there's 2 contacts, and when you press 2 metal contacts, and when you press the button, the metal contacts come together. And to us, that just seems like one motion. But as the metal contacts get close, it can actually cause the circuit to kind of connect and disconnect really fast. So at a high frequency, and you'll get like a high voltage, a low voltage, a high voltage, a low voltage, kind of like what you see on the right. And so this is really common with any physical button. This is like a physical limitation that you have to engineer around or like create solutions for. So this is a pretty common problem that you will encounter. And so how we fix this is we debounce the buttons, like Jordan said. So there are like firmware solutions as well. Basically how you program in what you read. You can program how to ignore certain readings and whatnot, but I'll be teaching you guys the hardware solution. And I think the common solution is using an RC filter, which Nita was talking about earlier, and a Schmidt trigger, which uses an op-amp comparator, which Nita also talked about earlier. And if you still don't understand how either works, it's fine. I'll just show you how the input, how the circuit changes the input to a new output and how that debounces the button. If you see on the right on the oscilloscope, wait, did you just get Zoom Premium like just now?
It says you just got a gift, so I guess it was extended.
Oh my God. I have no idea how that happened. We have Zoom Premium now, sick. Okay, yeah, so I'll be teaching you guys how we can stop this debouncing. And you see on the right for an oscilloscope, you see like kind of up and down that you might read on an oscilloscope when you test these signals, like you're just kind of prodding it. So starting with an RC filter, RC just stands for resistor capacitor, because all it is a resistor and a capacitor connected to the ground, and it filters out high frequencies. But basically how it does it is, I guess I can just show you guys. You can control what frequencies to filter out. But okay, let me just show you this first. So if you imagine this like really simple RC filter that I like quickly drew while Nita was doing her presentation, because we realized this is pretty useful. And so over here is the voltage that, so pretend this is the button. When I change the slider, you're getting a voltage. So that's basically the button. And test point over here is what we're reading. So if I move this capacitor away, and it's basically button resistor into the reading, so this might be a microcontroller or something, and I run the simulation, if I go high, it just goes high. If I go low, it just goes low. And a button basically goes high and low. There's no like in between voltage, but basically any reading you get from the button will, you see on the bottom, be that reading on the output. but I can quickly put this capacitor back in. And if I start the simulation, so buttons off at the moment, there is a bit of inrush. You'll probably learn about inrush later. Not too important at the moment, but as you can see, if I do like a really quick on, off, on, off, on, off, and then on, so I just like flick the slider a whole ton. You see, it doesn't actually go to the 3.3 volts. If I pause it here, you see these like bounces? That was the button doing the bouncing. But compared to not having the capacitor, where if I just bounced it, and you see these bounces each hit basically the 3.3 volts. So this capacitor, I guess I need to talk about this earlier, but how the capacitor works is it needs to charge up. At time equals to 0, when the voltage goes high, the capacitor acts as a short circuit, and as it charges up, I guess you guys will probably, you can do a bit of YouTube tutorial on your own, but it takes time basically for the test point to reach the full voltage. And that's how we initially prevent the output from getting the 3.3, even though the input is 3.3. So just one more time. Output goes 3.3, and the input will take some time because the capacitor needs time. Oh, will take some time to reach the 3.3 volts, and there's like a charging curve. Okay, back to the presentation. So yeah, basically when it's really high frequency, which basically the voltage switches a lot, an RC filter will kind of diminish that reading. So, and then like in the perfect world, the frequency should just be like 1, because it should only ever go from low to high once. And you can calculate what resistance values you need. So this is kind of like the engineering part of it. There's a lot of online websites. This is just kind of like the first one I saw when I typed in RC filter like calculator. But for example, if we imagine we want to filter out 100 hertz, basically bouncing 100 times a second, and let's say we have a common capacitor of 0.1 microfarads, which you'll see a ton. So like the general engineering question would be, what resistance value do you need to filter out 100 hertz if you use a 0.1 microfarad capacitor? And like the constraint of the capacitor isn't even that big a deal. You can kind of pick any like commonly used capacitor. You can pick any capacitor you want really, but generally you kind of default to the commonly used ones. And I just kind of inputted the two values to the top right. You see the frequency we want to filter out, the capacitor, and it'll tell me you use a 16 kilo ohm resistor and you'll cut off any frequency higher than 99.5. And so if this is kind of like the basics of how you use an RC filter. There's a lot that goes into RC filters, like transfer functions and row diagrams and all that, but you won't get into that for quite a bit, so don't have to worry about that too much. And then a Schmidt trigger. So when I showed you that RC filter and I bounced it a whole bunch, you still saw that the voltage was changing, just it never hit 3.3 volts. But we still don't want the voltage to be like between 3.3 and 0, because when you're working with a digital circuit, there's basically two types of signals. There's signal high and signal low. And high can be like, high and low are kind of arbitrary. They can be anything, but essentially you want an on or off. And basically it's, if you hit this voltage, it's on. If you hit this voltage, it's off. And like the in-betweens, you don't really want anything in between, because that's kind of like a no man's land. So how you do this is with a Schmidt trigger. And I won't really go into like circuit analysis of a Schmidt trigger, but essentially what happens is if you look on the bottom, so the top graph on the bottom picture is maybe real time what's happening to the voltage. So if you look, if you remember with my simulator, just at the bottom, you see like what's actually happening with the voltage. That's the top graph in the bottom image, and you see it bounces a bunch, it goes up, it goes down, goes all the way down, but there's two threshold lines. And what a Schmidt trigger does is it offers what's called hysteresis. The formal definition is the dependence of the state of a system on its history.
Oh, that's embarrassing.
But So if you imagine you start out low under the threshold and you go past the low threshold, you won't get a signal high until you hit the high signal, until you pass the upper threshold. And then even if you drop below the high threshold due to like noise or something, you won't get a low signal until you drop below a low threshold. So basically the Schmidt trigger allows you to change your varying voltage signal into a discrete kind of 1 or 0, basically if you're thinking in binary. So it's either on or it's off, and that's basically, and like physically, it's either above a certain voltage or below a certain voltage, and any noise causing it to drop between won't change the output. So there's like a buffer zone that kind of takes out the noise. And so now that you know these two, my professor likes to say tools in your kind of circuit toolbox, it's time to kind of go over how you implement them. And so basically when you start working on any circuit, you should start with a block diagram. And block diagrams are basically high level representations of a system, and it ignores small details. So on the right, it's some block diagram of like a chemical plant operation that I just pulled off of Google Images. But you can see how at first glance of the block diagram, you can see what happens to the steam or the gas solid feed, what machines it might go through, and you have absolutely no idea of like the settings on these machines, how they're configured, how they're managed, whatnot. But you can see the process at which the input reaches the output. And similarly, the bottom is, I just took this from BMS current sense. That's our battery management system current sense. It's a board that continuously measures the current coming out of our batteries. And so you can see the op amps, and you can see like blocks representing integrated circuits, or ICs. So you can see like the SPI IC, ISO SPI, the DC-DC IC, and it tells you absolutely nothing about like what resistance values you need to calibrate these, or what capacitors you need to put and where, but you can kind of follow the block diagram and see what this board is supposed to do. So basically, the block diagram of your current project could be something as simple as your 3.3 volts goes into 2 buttons, and those buttons go into a microcontroller, which turn on an LED. And so if you guys quickly think about it, how would you alter this block diagram to kind of include the tools that you now know to fix the problem of the buttons kind of bouncing? What time is it? 2:50. If there are no real guesses, it's pretty simple. Basically, the button goes to the low pass filter first, which goes to the Schmidt trigger. And this is basically, so you started out with a simple circuit, but the circuit had a problem. And what you do is you implement tools that you know can help fix this problem. But now it's the hard part. You know what tools you need, but you know those tools need specific values. So how you source your components, there's a lot of different websites you can go to. For this project, I'll just be using DigiKey, which is like primary source of electric components. But the low pass filter, you need a resistor and capacitor. And Schmidt trigger is an IC, an integrated circuit. So it's one of these black boxes with a lot of pins sticking out. And there's like many types of Schmidt triggers available. So I've kind of given you what tools you need to fix the problem. But here it's up to you guys to actually design the circuit. So your task is to find out what resistor and capacitor value you need for the RC filter. I guess I kind of showed you guys how to do that, but we'll say in this case, the frequency is, I don't know, 50 Hertz. I guess I should pick this down. But yeah, so imagine you had to filter out 50 Hertz or higher using the low pass filter, and also a Schmidt trigger. You want to find a Schmidt trigger that supports 3.3 volts. And also, I showed you in the previous diagram, there are 2 buttons. So just an additional constraint when you're looking for the Schmidt trigger, look for one with 2 inputs so that we only need 1 Schmidt trigger for the circuit. Of course, you could use Schmidt triggers with 1 input if you find that they're like way cheaper or whatnot, and you just need 2 of them. But for this project, try to find a Schmidt trigger with 2 inputs, and that supports 3.3 volts. And so what you're basically doing here now is going through data sheets and whatnot, which is a lot of what hardware engineers do, is looking for off-the-shelf options that satisfy what you need. And DigiKey, just maybe it's easier if I just show you guys. But DigiKey, you can type in Schmidt trigger, and basically it'll show you, like, there's a lot of different types of circuits. What we're really looking for is just gates and inverters, because this is the common thing that DigiKey falls under. But yeah, up here, you see there's a lot of different filters. Hang on. Okay. You see there's a lot of different filters. What generally, the first filter we do is active. You want to apply the active filter to DigiKey because if a part isn't active, it means that it might still be in stock, but it's no longer being created. So there's no support for it. If in the future we need this part, it might run out of stock. Or it might mean that it's not in stock, and if we order the part, DigiKey has to go and find who makes the part, and they have to order it, and it might take like 3-4 weeks. So you want to like apply the active filter, and then I guess you guys, it's up to you guys to look through the rest of the factors, the rest of the filters to kind of filter out what you need. And then down here, there's a lot of parts. You can just arbitrarily click on one of them. You can see a lot of the, oh shoot. You can see a lot of what you need to the right of it, but basically your work ends up being, you click on a part, you open the data sheet, and then you, if the data sheet wants to open, and then you read through the data sheet and see if it does what you need it to do. Does it support 3.3 volts? How many inputs are there? And there tends to be like typical applications too, but when you build your circuit, you need to see which pins do what. So I can just quickly scroll down. Oh, typical application. The input due to a push button switches multiple times, Schmidt trigger, and with an RC delay limit. So basically, you can see right here, under typical application of like just the first Schmidt trigger I clicked on, there's an RC. Here's the push button here. How do I draw? Oh, my chat's in the way now. This is embarrassing. Hang on. So this is your push button, and they have an RC circuit. And this is just like typical application, but this looks like a 1-input Schmidt trigger, so of course that's not what we want, but yeah, so you kind of get the gist of it. How do I get out of this? Yeah, you kind of get the gist of it. Look through the data sheet. Where is pin configuration? So you see pin configuration, it kind of tells you what each pin is for. And yeah, your first task, I won't have you do it in Altium yet, because we'll teach you how to use Altium. But for now, your first task will be to, so I guess I kind of just showed you guys how to do the circuit. I wanted you guys to try to figure out how to do the circuit yourself with the push button. But yeah, so I'll stop sharing there, but I will send a link to the slides so that you guys can look through it. And for now, us leads will sitting in this call if you guys want to work on it right now. Of course, that would be pretty cool. And you guys can just ask us questions as you go along. How do I link this? Yeah, you guys can go ahead and get started. If this was a regular term and we were actually in the garage, we would be sitting in the garage working on our own thing. You guys could be working on your thing. And basically we'd like come around, check on you, or you guys come up to us, ask us questions, or if you needed to go, you could go. Such and such, this is how This is basically how working sessions go, which is Saturday we do check-in and then we have a dedicated time where all of us are in one place. So of course, us leads are going to be here, and you guys can also try to work on it and just ask us if you have any questions. I'm going to try to copy a viewer link so you guys can go through it. Wait, Nita, if I give them a view link, are they going to be able to like get into the entire Midnight Sun Google Drive or no?
I don't know.
Okay, maybe I will download it as a PDF and send that.
Also, someone is asking if you could explain debouncing the buttons again and explain about the RC filters.
Okay, hang on one second. Let me upload the slides first. But yes, I can definitely re-explain it. All right.
Actually, someone just asked if design bays are open for people on campus. I can answer to that one. Right now for the hardware team, we are not opening up the bay for people on campus, just due to priority for the Mac teams to use it. We have a bay limit of like 5 people that can be in there at once. So for hardware, right now we don't have on-person tasks for everyone. So short answer for now, no.
Okay, so someone was asking to explain the RC filter again. Let me go back to share my screen. I can find the Zoom tab. Hang on. Can you guys hear me, by the way? Yeah, right? I didn't accidentally leave the call.
Yeah, we can hear you.
Okay. Do you see the circuit again? Oh, wait. I hate this website. How do I center? There it is. But basically, okay, wait, do you want us to explain like from the capacitor level, or do you think you can understand how the capacitor affects the circuit?
The original question says, how does the RC filter play a part in debouncing?
Okay, I guess it makes more sense for me to start with the Schmidt trigger, but so this picture, right? This picture of the Schmidt trigger. You see there's an upper and lower threshold. And so if we go to the simulation, take out the capacitor, and just pay attention to the scope, and I'm going to simulate the button by like flicking this slider for the voltage on the left. Like imagine the button bounces like that. You get multiple 3.3 volt readings because the output or the test point here just kind of mimics the input. And so if we go to the graph with the Schmidt trigger, that would essentially go above the upper threshold, below the lower threshold, above the upper threshold, below the lower threshold. And your Schmidt trigger is essentially useless because like all the bouncing action basically gives you the logic highs and logic lows that you don't want them to. And by having the capacitor in place, let me just reset the simulation again. When I go high and then low, high and then low, and then I can go high and low over and over again, and then eventually it should rest at high. Please stay there. Okay. You see all the bouncing, none of it ever actually reaches the 3.3 volts because of the capacitor. And like it takes time to eventually for the output to hit 3.3 volts. So all these bounces in the middle, if we go back to the Schmidt trigger slide, those will maybe go above the lower threshold, but they'll never hit the upper threshold. So it'll stay logic low because the capacitor, the capacitor essentially slows down the reading of the output from the input. So like all these bounces here, which without the capacitor would have been just like full hops basically from 0 to 3.3. I really should have used 5. Yeah, all these bounces that would have gone from 0 straight to 3.3 and completely ignored the Schmidt trigger threshold, by having the capacitor in the circuit, it essentially makes it so that the jumps don't happen immediately. So like there, I was at 3.3, and you imagine maybe the button like kind of lost contact for a little bit, so it bounced a bunch before going back up. Again, without the capacitor, if it did that, it would have went to 0, and car would have turned off or something. But with the capacitor, it doesn't go straight to 0 immediately, and the Schmidt trigger basically stops it from reaching the lower threshold and outputting the logic low. So essentially what the RC filter does, it slows down your signal. So like really high frequency bounces, because the capacitor makes it so that the output takes the output takes time to reach the voltage of the input. When the input changes really fast, it doesn't give the output time. And so the output doesn't actually read the 0 volts that the input might be outputting. English. Yeah, does that make a little more sense? Yeah, so the capacitor, it takes time to charge or discharge, and so that affects, I can slow the simulation down too, I think. Yeah, so if I go to 3.3, okay, maybe that's a little too slow. Yeah, you can see the current is flowing through the capacitor to the ground because it's not charged yet. But as the capacitor gets more and more charged, the output reads more and more of the voltage, because eventually when the capacitor is fully charged, it's essentially open circuit. So if we imagine the capacitor is fully charged, it's basically not there, and there's no connection to ground. How do I get to the page on DigiKey? So if you just go to DigiKey, and here, I should do it. If you go to back to homepage, so you can type in like resistor. Okay, I guess for now, you guys can just do resistor and capacitor values, but I'll show you here. When you type in resistors, there's a lot of different types of resistors. Capacitor and the resistor is the RC filter, and the RC filter feeds into the Schmidt trigger. So an actual Schmidt trigger is, actually I have it pulled up here. An actual Schmidt trigger is what you call an IC, or an integrated circuit. And basically it's a block where inside the block, there is more circuitry. Do they have a diagram of what's inside? Okay, yeah, here's the typical application. This is what I wanted you guys to kind of figure out yourself, but I guess this is such a common problem that they just have it right on the page. You can see the button goes to the resistor and the capacitor. Draw. The button goes to the resistor and the capacitor, which then goes to ground. This is the RC filter. And then this would have been the test point that we were representing here. What the heck? Oh my God. So yeah, test point is here, and then that test point would have gone into the Schmidt trigger, which is represented by this symbol. And so how do I get rid of this? Clear. Do they have a picture of the circuitry inside of Schmidt trigger? Did I miss it? Okay. Oh wait, no, I have it in my slides. But yeah, basically inside that black box is like circuitry. It'll have an op amp, it'll have resistors. And what I want you guys to do is find a 2-input one, which basically might have 2 op amps, and like it just doubles everything, and it'll have 2 inputs for 2 different buttons. So yeah, I'll keep talking about DigiKey for a bit, but if you look on, I just Googled resistor, And you see there's surface mount resistors, through-hole resistors, chassis mount resistors, etc. Surface mount and through-hole are probably the two most common that you'll see, as evident by the number of items there are. But what a surface mount resistor is like a really tiny block that will sit on the board. So if I go back to here, the 3D board. So you see where's my draw? It's like R2 here or C2 here. These really big capacitors. They come in different shapes and sizes, but these are surface mount. So basically the printed circuit board will have the pad on the very top layer, and you can solder on the component yourself. Stop drawing. Okay. And then through holes are basically like what you're more prone to seeing. This is the more common through hole, where there's like two legs, and your board might have a hole. Or if you guys have ever used breadboards, basically these are the things that you could stick into, like anything with a hole. And I can actually give you guys an example of a through-hole resistor. So this is pre-charge, and these really big white things are, how do I rotate? Oh, there you go. So you see, this is where's my draw? On the right here, this is a through hole. You see the holes here, and the legs you can bend to go through the hole. These are through hole resistors that go through the hole. And basically through holes, what they tend to be used for is just anything that's really high current. Because if you send really high current through something, through like a small resistor, like, how do I stop drawing? I don't know. Send like a really high current through a small resistor, like over here. This is gonna like heat up super fast and like blow up on you. So these bigger ones tend to be used for higher currents. And so that's through hole and surface mount. I don't remember why I was talking about these. Oh yeah, DigiKey. There's a lot of, why are my drawings still here? Clear. Yeah, so DigiKey, there's a lot of different types of things that you'll eventually like familiarize yourself with what types are what. If I go capacitor, you'll also see a lot of different types of ceramic capacitors, film, aluminum electrolytic. Ceramic is like the most common types you'll be working with, if it'll let me load. I'm not lagging for you guys, am I? I think my internet's a little slow. But yeah, lots of different types of capacitors, and at the top of DigiKey here, you can see there's a lot of filters for types of capacitors you might want. So of course, you want an active capacitor. Maybe we know we want the 0.1 microfarad, so we go find, or maybe we have a range. So we can go anywhere from, I don't know, let's say our boss tells us anywhere from 1 microfarad to like 100 microfarads. You can actually click, I guess, you can click the 1 microfarad, hold shift, I think. Please, hang on. Hello? Okay, let's say 3 microfarad. Let's go back to 100. Hold shift, click that, and now you've selected everything in the filter. So active, this capacitance, tolerance, you don't have to worry about too much. It tends to be plus or minus 1 or 5 or 10. And we're dealing with relatively low voltage, so you don't really have to worry about voltage. Operating temperature, don't really have to worry about. So basically, part status, and then the value range you want, you can hit apply. And that'll narrow down your searches. And then here you can see the prices of all of them, how many are in stock. Oh shoot. Yeah, price, how many are in stock, packaging, which I guess I'll go through next week, but packaging is pretty important. And I guess the main thing you guys should be looking for is Schmidt triggers. So you can type in Schmidt trigger at the top. Oh, already. Let me go back to the homepage. And the Schmidt trigger type you want is under logic, gates, and inverters. And so here you can see the filters. And so you can play around with what filters you want. Logic type, you probably don't have to touch too much, but mostly part status, I'll give you guys a hint, number of inputs, because I wanted you guys to find something with at least 2 inputs. Of course, you can apparently go up to 9 inputs, which I haven't seen. And it's kind of funny because you can see there are like 122 pages of Schmidt triggers, but if you click 9 inputs, there's only 8 products remaining. And that kind of gives you an idea. But yeah, maybe go to this page and look through some of the Schmidt trigger types, see what's generally seen in a data sheet. Yeah, let me know if there are any more questions, but we'll be sticking around, I guess, for a bit of time. And you guys can just work on this. It's kind of hard to hold working sessions when you're not in person, but stop share. How many are here? Nita, wait, Nita and Liam, do you guys mind just kind of, I guess, helping them whenever they need help? Kind of want to go eat lunch. Yeah, you can, if you find parts that you like, you can maybe send a link here, tell us why you like them, whatnot.
Would Slack maybe be easier?
Sorry?
Would Slack be easier?
You can, okay, it's kind of weird that our class Slack channel has both firmware and hardware, because I don't want to like flood the firmware people with like random discussion. But yeah, if you find like good parts to use and like why you want the part, typically what'll happen in the job is like your boss will come and tell you like, I need this application done. Like what I literally was doing this last week where I can close this, where my boss, we needed ultra low power boost converters because he wanted to be able to charge a battery using voltage from temperature differentials. If you guys didn't know, if you have like an object with a temperature gradient, so like one side's hotter than the other, you'll actually generate a really small voltage from that. It's called the Seebeck effect or something. But yeah, without actually going into too much about what the company is working on, they wanted to charge a battery using like waste heat because one side of something was hotter than the other, but the voltage it generated was like 1 microvolt or something, like unbelievably low. You're never going to charge a battery with that. But there's this wonderful IC called a boost converter. It's usually buck boost or stuff like that. But basically it steps up your voltage. And to deal with like 1 microvolt, you need really particularly made converters. So I basically spent a few hours on like DigiKey, or another common website is Mouser Electronics. You can find a lot of components here that maybe aren't on DigiKey. Yeah, I spent a lot of time just kind of looking through. I created a spreadsheet with a whole bunch of different types of components. And basically I had to present to them, hey, look, I recommend these 3 because this one is the cheapest, but this one has built-in safety functionality, but this one has a much lower voltage range. So in case the voltage we're expecting was even lower, stuff like that.